Welcome everyone to Contemporary Math. We want to take a look today at apportionment methods now that we've seen some voting methods. And apportionment methods are really a way of distributing things, whatever they are. So, for example, when you get Halloween candy, yes, it's been a little while since Halloween, but not too long ago. When you get Halloween candy, some people, some families, what they do is they find that not all the kids got the same amount of candy, and so they make everyone dump it into a pile, and then they distribute the candy evenly to the kids. That wasn't my family, but maybe that was your family. Me and my sister, we dumped ours into two separate piles and then traded if there was stuff that we wanted. Anyway. So, but this distribution of candy to the kids is an apportionment, okay? That's the idea. And in a political sense, right, in our government system, we have state representatives in the House and in the Senate. And so we have, let's see here, we have a couple different ways that we are represented, and what we've done is we've apportioned a certain number of seats to each state. So let's take a look at what I'm trying to say here. So when the Constitution was written, there were a couple of things that were considered. Each state should have equal representation. So, for example, each state, I believe, has 2 seats in. Now here I'm doing really poorly. House versus Senate. We have 2 seats in one of those, and then in the right. So they have equal representation. We all have the same representation, but in the other, right, we have a certain number of seats, and those seats are distributed among the states, so that way each state has a representation that is proportional to its size, its population size, that is. So we have these 2 different types of representation, and to handle that, we ended up with 2 different governing bodies to help us. All right. So this is kind of the motivation for the section. A lot of course, voting is clearly a government topic. So here, apportionment, a lot of it is viewed through a government topic as well. And you'll find that the text that we read might not match perfectly with what we're doing in terms of how it's discussed and presented, but that's because I'm using a variety of texts here. So feel free to read the textbook, so that way you're getting maybe more of a full picture, possibly a better understanding, because what we're going to take a look at in this section is just a nice introduction to apportionment methods. And there are a few of them. We'll take a look at 3. I'll have you guys take a look at 1 on your own as well. But to begin, we'll start with some simple representation. Oh, hey, look at here. I have in our notes the Senate. In the Senate, each state receives 2 senators, and then in the House of Representatives, each state receives a number based on the population. Excellent. So I may not have remembered off the top of my head, but it was here in our notes. Excellent. So apportionment methods. Let's take a look at an example. Okay, this example is set up for convenience. It's supposed to be very, very nice, so that way there's no issues, no concerns, no question about how to distribute the things we're distributing. So if we look at a problem facing the First Physicians Organization, a healthcare provider that operates 5, not FICE, 5 medical clinics. The organization has recently hired 60 doctors. That's a lot of doctors. And they want to distribute those doctors to the various clinics. But the question is how do we distribute the doctors fairly? So they're choosing to distribute or apportion the 60 doctors based on the number of patients who visit each clinic in a week. Okay? So this is what we're saying is a fair way to distribute them, much like the House of Representatives, where each state has a number of them based on the population of the state. Excellent. So to help us decide, what we want to do is we say whatever percentage of the patients that Clinic A sees, that's the percentage of doctors that they should receive. So Clinic A has 60 out of the total 600 patients seen in a week. So this is 1/10 or simply 10%. So Clinic A should receive 10% of the doctors. And 10% of 60 doctors would be 6 doctors. So that is Clinic A should receive 6 doctors. Excellent. Now let's repeat that for the remaining 4 clinics. So a few to go through here, but that's okay. So Clinic B sees 120 patients. So 120 divided by 600 is equal to 1/5 or 20%. And in this case, let's see. So Clinic B should receive 20% of the doctors. That is Clinic B should receive, let's see, 20% of the 60 or 1/5 of the 60 doctors would be 12 doctors. Okay, that's not so bad. So continuing on with that, we would have for Clinic C, they see 180 of the 600 patients. Well, 180 out of 600, that is 3/10 or 30%. And with that, well, we would say that Clinic C should receive 30% of the doctors. That is Clinic C should receive, let's see here. They should receive, that'd be 18 doctors. Excellent. All right, let's take a look at our next clinic. That would be Clinic D. They see 60 patients a week. So 60 out of the 600, again, is 1/10 or 10%. So Clinic C, or Clinic D here, should receive 6 doctors, like Clinic A did. And then for Clinic E, they see 180 patients as well. So 180 out of the 600, we already found that to be 30%. So Clinic E should receive 18 doctors, like Clinic C. Excellent. So what we should notice there is that we actually have found that we've distributed the 60 doctors, and we've done that by calculating the percentage of patients seen by each clinic. Each clinic received that percentage of doctors, so we should find that the total doctors distributed was exactly the 60 doctors that we had. So 6 plus 12 is 18, plus 18 is 36, plus 6 is 42, plus 18 is in fact 60. So we did in fact distribute the 60 doctors. But if we notice, we could have found the number of doctors distributed to each simply by dividing by 10, right? 180 patients divided by 10 gives us 18 doctors. Well, that's interesting. So let's make note of that. So notice that we could have found the number of doctors for each clinic by dividing by 10. Well, that's kind of interesting. Well, what it is we've taken the 60 doctors and we've multiplied by 100. We multiplied by the number of patients seen each week divided by 600. This is the percentage of patients seen each week, and this is the number of doctors we have to distribute. Well, that's the same thing as taking the number. Let's see if I can rewrite this appropriately here. That's taking the number of patients seen each week and multiplying it by 60 over 600, which is taking that number, and if we were to simplify it a little bit here, that would be multiplying by 1/10, or simply taking that number and dividing it by 10. Okay, so what is this here? So when I go from number times 1/10 equals number divided by 10, I can think of it as multiplying across, or I can think of it as, and I'm taking this number and I'm dividing it by the 600 divided by 60. Okay. So this, if we take the number of patients seen each week divided by this number, we get the number of doctors that go to each clinic. And this number here is of particular interest to us. And this number is called the standard divisor. So rather than calculating the percentage each time, what we do, or what we can do, is we can simply find the standard divisor, take the number of, or take the total population and divide it by the number of things to be allocated. That's this number here. So again, that's called the standard divisor. Okay, standard divisor. And then if I wanted to, I can take the number distributed, or the number we have in each particular group, so the number of patients seen each week by a particular clinic, divided by the standard divisor to find how many should be allocated. And that number is called the standard quota. So we take the population for a particular group, number of patients seen each week for a particular clinic, divided by the standard divisor, and that gives us the number of patients, or the number of doctors to be distributed to each clinic. Okay, So as we move forward, we can use the standard divisor to find the standard quota rather than computing percentages for each group that we are distributing to. All right, so that's the idea of what we want to do. But of course, things are going to be a little bit more complicated. And the reason things will be a little bit more complicated is because most of the time, what we have to distribute won't divide nicely. Right, 180 divided by 600 is 30%. Multiply that by, let's see, 50 instead of 60, and the numbers no longer work quite as nicely. Right, 20% would still be nice, and actually 30% would still work out quite nicely. So let's say 51. There we go. If I multiplied that by 51, it no longer multiplies out nicely. Right, we would have a partial there, and that wouldn't be so good. So that's what we'll see in the following examples and in the following apportionment methods. So we'll repeat this example in a moment to talk about things a little bit further, and then we'll take a look at Hamilton's method and several other methods for apportionment. All right, so I'll see you guys again soon in just a moment to take a look at the same example with a different number of dots.